Section 1. Introduction to Quantum Randomness and QRNGs. Quantum randomness is a concept that stems from the heart of quantum mechanics, a theory that describes the fundamental nature of the universe at its smallest scales. Unlike classical randomness, which can often be predicted with enough information, quantum randomness is inherently unpredictable. This unpredictability makes it a prime candidate for generating truly random numbers, a task handled by quantum random number generators, or QRNGs. QRNGs harness quantum phenomena to produce random numbers. These devices are crucial in fields requiring high levels of unpredictability, such as cryptography and complex simulations. Their core advantage over traditional methods lies in their ability to generate numbers that are impossible to predict due to the fundamental laws of quantum mechanics. The basic working of QRNGs involves exploiting the random behavior of quantum particles, such as photons or electrons. Each particle's state is uncertain until it's measured, leading to genuinely random outcomes. This inherent randomness is what sets QRNGs apart from other random number generators and positions them as a pivotal technology in securing digital communications and data encryption. Section 2. The role of photon polarization in QRNGs. Photon polarization is a quantum property that QRNGs utilize to generate randomness. When photons are emitted, their polarization, the orientation of the waves, can be in any direction. This direction is undetermined until the photon interacts with a polarizer, a device that allows photons of certain polarizations to pass through while blocking others. The random orientation of each photon's polarization makes it an excellent source of randomness. To generate random numbers, QRNGs typically shine a light through a polarizer and then measure the resulting photons. The setup might include a beam splitter to enhance the randomness by sending the photons through different paths. Each detected photon is then assigned a binary value, 0 or 1, depending on its polarization after passing through the polarizer. This process is repeated many times to generate a sequence of random numbers. The beauty of using photon polarization is that it's governed by quantum mechanics rules, which state that the outcome, in this case the direction of polarization, is fundamentally probabilistic. This means that it is not just unknown, but unknowable until the measurement is made, ensuring the randomness of each number generated by a QRNG. Section 3. Comparing QRNGs with classical PRNGs. Classical random number generators, or PRNGs, rely on algorithms to produce sequences of numbers that appear random. These sequences, however, are actually deterministic, meaning they can potentially be predicted if the algorithm and its initial conditions, or seed, are known. This predictability can be a major vulnerability in systems that depend on unpredictability, such as encryption algorithms. PRNGs often use mathematical formulas or predetermined processes, which can repeat after a certain period. These limitations make them less suitable for applications requiring high levels of security and randomness. In contrast, QRNGs do not suffer from these limitations because their randomness is not derived from an algorithm, but from the inherent unpredictability of quantum phenomena. The fundamental difference between PRNGs and QRNGs is the source of their randomness. PRNGs simulate randomness through computational algorithms, while QRNGs exploit the natural randomness of quantum mechanics. This makes QRNGs more secure and reliable for applications where true randomness is crucial, such as in cryptographic systems and high-stakes decision-making processes. Section 4. The security benefits and future of QRNGs. The unpredictability of QRNGs offers substantial security advantages over classical methods. In cryptographic systems, the randomness of keys generated by QRNGs makes them extremely difficult to predict, thereby enhancing the security of encrypted messages. This level of security is crucial in an era where digital data breaches are common and can have severe consequences. Beyond security, the potential applications of QRNGs are vast. They are being explored in fields ranging from scientific research to gaming. As technology advances and the demand for secure digital communication increases, the importance and utility of QRNGs are expected to grow significantly. Looking ahead, the development of QRNG technology promises to revolutionize how we handle data security and privacy. With ongoing research and improvements, QRNGs could become a standard tool for ensuring the highest level of randomness and security in various technological applications. Their ability to harness quantum mechanics not only secures our digital world, but also opens up new avenues for technological advancements.